because this course doesn't have that as a prerequisite. So, and that'd be utterly unfair if I did that. You imagine. uh, okay, so this right here is the blood glucose readings, by the way. And why do you do varying readings indicate? Well, typically, if you have large swings, it would indicate things like poor technique, malfunctioning meter, but could also indicate a very serious health issues that your blood sugars are skyrocketing and then crashing back down. It means your body is not properly controlling that, right? So the manufacturers of blood glucose meters actually recommend running a control sample to test one's technique and glucose meter. These are usually provided as little calibration samples. And what you would then do is you'd measure the control sample. Usually you'd stick it in and measure it several times. It actually usually does several readings whenever you do one of these, by the way. People don't often realize that, but you know how it's going like tick. Have you guys ever seen one of these used? You touch it to your blood, and that's what they're doing here. See that? And it has the blood sample on here. And then what you see is like there's a tick, 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 tick. Those are usually different scans of it. So it usually does multiple scans of this. This is usually an electroanalytical technique right here. And what you're looking at here is then they take several measurements, they take the average, and then in this case, we have a control sample and we see it's a little bit low, isn't it? So our average is a bit low. And so this is how you determine if these measurements are correct. Anybody seen the new meters they use, where they actually put them in? Yeah? No? Okay. So the new meters are like little pins, essentially, that penetrate into you. You put them on the upper arm. And then usually once people have used them for a bit, they'll put a sticker over it to keep it in place. Okay? And one of the reasons for that is because they're very, very prone to coming loose and then having problems reading and giving just wild readings all over the place. Okay? And then needing recalibrating. They're actually kind of crappy in terms of that, though very convenient because they continuously read on your arm. So statistics actually gives us some, let's call them tools, but also they act a bit like rules. Okay? So they act sort of like rules that you can use to guide yourself, but also tools to accept conclusions that have a high probability of being correct and reject conclusions that have a high probability of being incorrect. Now, one of the problems with statistics is garbage in gives you what? Garbage out. And so there's a few fields that have been using statistics lately and failing spectacularly. Okay. I'm going to avoid talking about those fields because it's a bit of a hot button issue. But just know that 66% of one field of all the major studies done in the last 20 years were based on bad stats. Okay. And so the field basically has melted down, just destroyed. And that person that had done 6 of the publications of the 10 most seminal of the last 20 years actually faked their data. So, and nobody had bothered statistically analyzing their data whatsoever. So, that one was a University of Florida, by the way. Yeah, that guy was from University of Florida. Yeah, really, really bad. Anyways, I'm gonna avoid naming the specific field. You can look it up if you want. It was a disaster. And we've had about 5 or 6 of those over the last 10 years. Okay? Where it's complete meltdowns of the field. Okay, this is a Gaussian distribution. Have you guys ever seen this before? Okay. Who here thinks they happen everywhere all the time? They happen a lot. Okay? But biology has a tendency to use these a lot and really, really depend on them. And professors tend to have a tendency to use them a lot and depend on them every. Okay? But in reality, Gaussian distributions are less common than professors like to think. Okay? And so we typically use these a lot in places that they really shouldn't be used. For example, grades. Everybody knows your grades are actually typically done as a Gaussian distribution, right? Most people curve them that way. Um, grades are not Gaussian distributions. They're bimodal distributions, meaning they have two peaks. They do not have one peak. So very much not a Gaussian distribution in most cases. Okay? You have to have a very similar class of very similar people for it to be Gaussian. Now, the results tend to cluster symmetrically in a Gaussian distribution. So if you do an experiment, it's been repeated many, many times. And if the errors are purely random, so the differences are purely random, then you will get a Gaussian distribution. The results will cluster symmetrically around the average value. So we're seeing that right here pretty nicely, right? The more times the experiment's repeated, the more closely results are going to fit the Gaussian distribution, i.e. that ideal bell-shaped curve, and everybody can see the bell-shaped curve, right? This is the difference between a Gaussian distribution and other distributions, is the bell-shaped curve, and you tail off, and you actually usually never actually reach zero on most Gaussian distributions here. It just goes very, very tiny numbers. So if you repeat an experiment 3 to 5 times, is it going to fit the Gaussian distribution perfectly? No. No, it's going to be like this, right? So this would be 20 times of this experiment. And you see, it doesn't really look that Gaussian-like, does it? Okay? But when you take the average of all those values, it actually gets reasonably close to your Gaussian distribution. Okay? So if we take a small data set, we can estimate the properties of a hypothetically large data set and tell what sort of offset it might have. Okay. Now, one of the things you need to be very careful on here is when you take a small number of sets here and it doesn't look so Gaussian distribution like, what does that mean if you take more sets and it stops looking, it even looks further from being a Gaussian distribution? What if we did this and it started developing two peaks instead? It's actually bimodal, isn't it? It isn't a Gaussian distribution. The factors underlying what you're looking at are not purely random. Okay? They have groupings within them. So that means that there's another factor at play, right? That you have not controlled. Okay? I just taught you a super important thing that will cause you to not destroy your career. Look at that. We solved major scientists fucking their careers up in like one session here. Okay. Okay, so the mean or average, these actually have slightly different meanings per se, but for us, they're usually synonymous. The mean and average, that's the sum of the sets of results divided by the number of values in the set. You guys probably already know this. I'm going to kind of not go more into it. As we increase our number of sets, this right here being the mean, is going to approach the true value, okay? And that's that mu right here, okay? So as you gain more and more sets, you're going to approach the mu, okay? Standard deviation. This can measure how closely data are going to be clustered around the mean. Notice the difference in terminology again, okay? So you have this standard deviation right here, which has n minus 1 down here. So these are the sum of the differences between your individual values and your average, right? Notice it's the average of the one you're using, right? Not the mu, okay? And then you're going to square those. Can you get negative numbers out of that? Okay. Notice that these are actually squared and then added together, okay? And then you're actually going to take the square root at the end, okay? And these are root square means. That's what those are up there. Now, this number down here is n minus 1. N is the what's? Number data set, right? Minus 1, because we want a slightly larger number because we're not an infinite data set, okay? We don't necessarily have every single repetition of this we Okay. Now, as the n increases, we're going to move from a standard deviation, which is S, to this, which is sigma. Okay. That's probably the standard deviation you've seen before. And that's the one that would just be n down here, in case you're wondering. Okay. And so there's a very important difference in these. Now, notice that when we're looking at standard deviations, this is going to be from the average, which is the middle, the highest point of our Gaussian curve. This is actually going to tell us the width of that Gaussian curve. Okay? That's what a standard deviation shows us, right? So, for example, the standard deviation here would be to 66% of that population within that curve. Okay? Can everybody sort of see that? Okay. Right. If we go 2 standard deviations out, that's going to be a larger percent different of that curve. And as we go further out, we're going to get larger amounts of that curve, right? Is everybody okay with that so far? Have you guys seen t-tests before? Who here's seen t-tests? Nope, not yet. Okay. All right, so this one's the value determined. That's your mean or average, okay? Okay. What's going to happen to the standard deviations as you get more sets, by the way? They're going to get smaller. And so what's going to happen is your curve here is actually going to thin out, isn't it? Okay, so again, precision, accuracy, and trueness. Remember those terminologies that we used before? Okay, did anybody have any issues with those, not understand those? Mm-hmm. Okay, so accuracy is how close you are to the trueness. Okay, it's like you could have incredibly imprecise data that are just clustered in such a way. Let's say that's the true value. If they average right on the true value, you achieve the true value, right? Despite the fact your standard deviation and precision are going to look off. Okay. Okay. Precision, on the other hand, is how tightly they're clustered. And so you can be very, very precise and be completely off. And that would be the sort of experiment where you have very little random error and you have lots of systematic, right? Does that make more sense? Trueness is actually going to be the closeness of the mean value to your true value. This is assuming the random uncertainty, though, is 0. Okay? So it's how close it is to that true. Okay? No problem. It would be the actual number, like the absolute truth. Yeah. I want to break you apart from the table because realistically, you guys are going to start doing things that are not on tables. So it's somewhat difficult to actually know the trueness of something. What you have to do is you have to use these other things to determine trueness. And we'll actually talk a little bit about this is why we have statistics, is it's going to give us indications of how likely we are to the true value. Okay? It's going to help us with that. It's not going to actually give it to us, though. If there are things we don't know about the system, we could be far off trueness. Okay? And so that's actually the difference between the accuracy and trueness here. Again, accuracy is our nearness to our perceived true value. Our trueness would be that closeness of that mean value to the true value, assuming the random uncertainty is 0. So we absolutely zoomed 100% in. Okay. So experiments that are small standards of deviations are going to be more precise. Standard deviation is a direct correlation to precision. Okay. It doesn't actually tell you anything about the trueness or accuracy. Okay. So remember that in your heads, I want you to have a clear divide between the preciseness and the accuracy. Okay. You can think of also trueness is if we had random error, we're going to approach trueness the more repetitions we have. Okay. Whereas accuracy doesn't really matter for that. Accuracy just is as our value. Okay. So again, if I have a lot of variability, my standard deviation is very large. Does that actually tell me anything about the accuracy? No, that doesn't actually tell me anything about the accuracy. What it does tell me, though, is if I'm going to try to find accuracy, I probably, if I'm going to have a good accuracy, a lot of trueness to my value, I probably need to do the experiment a lot of times, don't I? And get a lot of results. Okay. Now, express the mean and standard deviation. You always express them in this form right here. And so this right here is the mean, plus or minus the standard deviation. And then you usually actually express an n equals right here. But sometimes people will actually express the percent likelihood instead. Okay? That your true value rests within that range. That's that t-test information. Sometimes they express that there instead. You should actually express the number of observations there. But so the average and standard deviation should both end in the same decimal place. This standard deviation is actually the one that's telling you what the correct number of significant figures for your average should be. Okay. Now, let's say I had actually mentioned this to you, Will, but it's an important thing to make sure it has. What the hell? Stole the markers. Okay. Something. Oh, here we go. I stole the last marker apparently. I'm gonna put next. All right. So let's say we had a 0.051 plus or minus 0.001. How's that? Looks good, right? This one was actually 1, 1. So typically, if you're going to represent the uncertainty by that, what you would actually do is you'd have another number here as well. Okay? So that your decimal places match up. And that actually can happen sometimes where you're using these standard deviations. If you do like a 2s, 3s instead, so you have a higher percent chance that these values will be larger, but you want to give more decimal places because likely you've overestimated. You're being conservative. Okay. And those extra decimal places are usually something that's significant to you and you want to actually represent. Okay. All right. What if I have a number like this? Does that make any sense at all? No. But wait, that goes out of 0. Dr. Clausen, I have a 0 there. The hell, man? So what should you do? You could round. You could round it up to 0.1 plus or minus 0.1. That is correct. Not usually what people do. So what you would usually do is you would go ahead and put this next digit like that. Okay. And so that would also be correct as well. Mhm. Mhm. Yep. Yep. So let's say that this was 0. Still. Yes. Yeah. If you have a decimal place here, what you do is if you have a decimal place, you go all the way out. Okay. You see the decimal place? You go all the way to the left, and then you start working your way in. Not significant, not significant, significant, everything after significant. Okay. They mentioned it just like Exactly. Top five. Yeah. 1, 2. Oops, I missed. Okay, yeah. I miscount. Thank you for asking. Nope, I miscounted. Okay. Did that make sense so far? Yeah. All right. Now, again, this is decimal place, by the way, because why is it decimal place? Addition, subtraction uses what? Decimal place, not sig figs. Okay. So be careful about that. Okay, so let's talk about degrees of freedom. This is actually right here, the degrees of freedom. Okay. Now, this is degrees of freedom everywhere in science, right? This does not just come from this class. Okay. So when you see degrees of freedom from now on, what is that? D, degrees of freedom, equals n minus 1. Okay. It's the number of things, in this case, number of observations, minus the number of parameters that are estimated from those observations. And so that's minus 1 in this case. Okay. Now, the variance, this can be the square of the standard deviation. So variance equals, now sigma oftentimes is going to be used interchangeably with S. They are not the same things. Sigma is if you have an infinite number of observations, right? So if they want to mathematically represent standard deviations, they oftentimes use sigmas because they're like the highest order of standard deviation. Okay. S just means you have a limited set within sigma, right? Relative standard deviation, that's going to be the coefficient of your variation. Also, that's the other term for it. The standard deviation is going to be expressed as a percent of your mean value. So again, you take that standard deviation, divide it by the mean, times 100%, so it's a percentage. Okay? And that's relative standard deviation. Now, note that there's actually two relative standard deviations. You're almost always going to hear relative standard deviation. They mean this. Okay? This is like 99% of the time. Technically, relative standard deviation could also mean the fractional one. And that's actually the correct one, by the way. So everybody uses it wrong all the time. This is relative percent standard deviation, right? But everybody drops the percent because nobody ever wants this non-percentage, right? So do be aware of that in case that language starts both coming up, okay? That there is a difference. It's not difficult to go back and forth in them, but there is. Okay, so find the average, standard deviation, and relative standard deviation for these numbers right here. Did you guys want to practice this, by the way? Okay. No? Okay. Yeah, just okay, so I'm totally fine with you guys practicing this. There is no like negative opinion about that. I'm just gonna remind you that like won't be able to cover the entire 100 slides. So yeah. So if we ever get to one of these and you're like, I don't need practice on that. Just let me know. For example, in my typical general chemistry, when I taught that, I would have people would have done this 10 or more times. If you go back in my old slideshows and my old lecture notes, people always wanted to skip this stuff. Okay. I'm going to give you another minute or so, just try to set everything up if you don't have time to actually do the math. And do a bit of math just to make sure you know how to use your calculator. Okay, folks, I'm going to start moving forward. We'll compare how your math is set up versus mine. Okay, so the average, you just add the values together, divide by 4 in this case, because there's 4 items, right? Don't forget to do all the addition first. Sometimes people forget and try to plug it in the calculator. I would actually do this two separate steps in my calculator. Add these together, enter, then divide by 4. Okay? Because if you do this in the wrong order, you'll only divide one thing by 4. Okay. You'll get a value that's somewhere in between all your other values. This is 823.2 in this case. Notice we've went ahead and added an extra decimal place here, so our calculations don't have such a wild swing on. Okay? Okay, so once you have your average, the next thing you're going to do is you're going to set up your standard deviation formula. Again, I would actually do this in my calculator as several steps. Okay? And so that's going to be the individual values minus the average, right? Then you're going to take that value and square it. Okay? So you do that subtraction, then square it. You're then going to take these values and add them together. Notice you'll do that 4 times and add them together, right? Will you get negative values before you square them? For sure. Okay? For absolute sure. After they're squared, no. No negative values because it's negative times negative, right? By definition, that average has to be high for some, low for some, right? Does it actually matter if you flip these values and do it the wrong way? Average minus the individuals? No, doesn't matter. Not at all. Then you're going to take it, divide it by degrees of freedom, which is the 4 minus 1 number right here, so 3. Then you're going to take the square root. Is there an easier way of doing square root other than typing in that thing? Yeah, to the 1/2 power, right? So 0.5 power. Okay, that does the exact same thing here. Okay, so once we have the standard deviation right here, what's the next thing we do? Yep, just take that, divide by the mean. This right here will be the absolute error, by the way, as well, in this case. And so we're going to take that, divide it by the mean, get it in percentage, so times 100%. Yeah, so this right here would be the absolute error in this case. So, and then the relative error is this one here, which is the percent, right? Yep. Is that making sense for everybody? Okay, fantastic. Now, when we do this, and we're doing this on a spreadsheet, this becomes exponentially faster, okay? Because we can just put our values in. I recommend labeling so you can keep track of what is what, but we put our values in, we type average and then highlight our values. That gives us the average. We then type this right here, which is stdev.s. Be careful about not doing the .s. There's 2 types of standard deviations. One if you have the entire population, one if you only have a subset, right? That's that n minus 1 versus n. We almost always want the n minus 1. It's very rare for us to have our entire population, okay? Because that would be an infinite number of tests, right? Now, we oftentimes count things that are like 1,000 or 10,000 tests as being the whole population, okay? But technically, they're not. We're just approaching it. If you do this, by the way, you don't have to include the mean. Be careful about that. You just include the individual values in this, and it'll give you your standard deviation now. Okay? Anybody know how you do a 2s or 3s? 2 times standard deviation, 3 times standard deviation? Yeah, just put it 2 times up here, right? Then congratulations. Or back here, wants to. Okay. All right, so let's talk about non-parametric statistics and box plots. So this right here is going to be statistical tools that assume the data follows the Gaussian distribution. Data can again be asymmetric though. We can have log normal, bimodal, Poisson, and there's actually a bunch of others, right? Did you guys go through all those in stats? Huh? Did you? Yeah. Is that a loved, actually loved, or okay? Fair. Okay, so the symmetric Gaussian distribution median is going to equal the maximum and the mean. Okay, so for the median, maximum, and the mean are all going to be the same things if you have a symmetric Gaussian distribution. Okay, if you have an asymmetric distribution, the median is not going to represent the maximum and the mean. Those are not going to all be the same things. Okay, they will actually be different values, right? For example, everybody's heard of the mean versus median incomes in the United States. Okay, they are not the same numbers at all, right? Or house size, also completely different numbers. And so they are not randomly distributed, are they? Okay, which is pretty obvious if you start thinking about them. The fact that anybody tried to use a symmetric Gaussian for that was freaking stupid. But people have for many years and still do. Okay, so box plots are actually going to summarize these non-parametric statistics. Right here, you have your box plots right here, and they're going to extend from your lower quartile to the upper quartile, and this is called the interquartile range, and it encompasses the middle 50% of the distribution right there. Okay, and so you've seen these box plots before. They're actually helping you determine if the Gaussian fit is actually supposed to fit. So again, this is your mean and standard deviations. Do not round off during calculations. Retain all extra digits in your calculator. Round proper. I think you got that right. Okay. So this is actually the formula for a Gaussian curve. If you were to try to plot this just with x and y, this is how you'd plot that. Okay. If you ever try to plot this in a Excel or something, you want a Gaussian curve, this is how you can do that. Okay. You can actually set this up in your cells in Excel and have it automatically change with your standard deviation and average as you put in values. Okay, which is kind of cool actually. So this is the formula again. It's y equals 1 over, what's that value again? Standard deviation, but this would be for your whole population, right? Okay. And then it's square root of 2 pi. Does everybody know how to do that on like Excel and stuff? For pi, you actually put in pi in parentheses, and that's how you get pi. Okay, you can actually just put the value in 3.14 on the number of decimal places you want as well. Then this is times e. This is to the power of this entire thing up here. Okay, and so that is a negative in parentheses x minus. Notice what that is? The mean, right? But the mean for what? The whole population. If you had infinite number of observations, right? Okay, and then this is then going to divide it by 2 and sigma again, and that's squared. Okay, does anybody notice what this looks like up here? It looks a lot like what you get the sigma from, don't you? That's your square differences. Okay. So again, you can express these deviations from the mean value in multiples of z, and this would be z right here. Z is actually this number here. So it basically is in multiples of how your thickness compares to your standard deviation. Okay? How far off you are compared to standard deviation. So this is z again. It's going to be your individual values minus your mean here divided by the standard deviations. Okay. This is actually your z's here. Notice it's a way you can standardize those standard deviations off. Okay. So you can talk about 1z, 2z, 3z for different standard deviation values, right? So if you had a 1 here, what does that mean about this thing here? That the difference between these values is a whole standard deviation out. Okay? So 1 here would be an entire standard deviation out from the mean. Can you see that? A 2 is 2 standard deviations out from the mean. A 3 is 3 standard deviations out from the mean. Everybody understand those okay? Okay. Okay, negatives, just the other side, right? Okay, anybody have any questions there? Okay, that's a place people usually get caught on and have a trouble, okay? This right here is actually what this table helps you with. So it's the ordinate and area for the normal Gaussian error curve. Again, there's the Gaussian formula. And so these are going to be in Z's right here, multiples of Z's. Everybody see there's footnotes here? And so our footnotes are right here. That's the formula for a Z. Remember, those are multiples of standard deviations out. Okay? Okay. Now, when we look at these multiples of standard deviations out, what we notice is that we go over here to 1, right? We're 1 standard deviation out. Okay? It's the thing you've probably seen the most of being reported. Okay? Now, keep in mind, this is absolute value, right? So we're only on one side of this, aren't we? Okay? Now, once you actually look at that, what would the area tell you about this? What's the total area under a curve? It would be 1 here, wouldn't it? Can you see if you took all these numbers and added them, doubled them, they eventually, if you go to infinity, go to 1, don't they? See that? So what we're seeing here is we have an infinite number of z's. We have the entire Gaussian curve under our deal. We have all of the results under. Okay? Can everybody see that okay? All right. So 1 standard deviation out is going to give you about 60, a little over 67, 68%. Okay? So about 2/3, a little over that. Right? And so if we're 1 standard deviation out, we will have 2/3 of the possible results that would be under that Gaussian curve, right? What if we're 2 standard deviations out? For we do a 2 sigma, a 2 standard deviation. We take that number there, we double it, right? Anybody notice that's just slightly over 95%? Okay, if you've ever seen a t-test, you're going to recognize these values immediately, because that's actually the values that are coming up on t-tests. You have a 95% confidence interval. That's because you used a 2 sigma, 2 standard deviation. You have a 66% confidence interval. You have a 1 sigma, 1 standard deviation. Okay? And that's actually how these represent. So if you wanted like a 99% chance that everything's going to fall within, your true value falls within, you're actually going to want a 3 sigma. And that's how you would get plus or minus 3 sigma, 3 standard deviation, 3 times standard deviation. Okay? So here, if this is 1 standard deviation, what's my chance that the true value falls within my range? Again, I said is 1 standard deviation, right? So I come up here to 1. Over here's the area. Okay? I have the plus and minus here, so I'm going to times that value by 2, right? Because I'm doing both sides. Okay? And so I have about 2/3, right? It's about 68% chance that my true value falls within this interval here. Okay? Now remember, when you look at this interval here, what does this actually mean? I have an interval that ranges from 0.0 through to 0.0. Again, didn't I? That's where I have a 66% chance, or 68%, excuse me, chance of my true value being in that range. Okay, assuming everything else is fine. Now, if I double that, I end up with a 95% chance, right? Triple that, 99%. Usually people don't go further than that just because it's just not necessary. But if you have tens of millions of times you have to get this to work, you have to go further. Okay. Does anybody have any questions there? Okay. Did anybody catch that there's a real irony that you may have noticed developing here? Has anybody ever looked at a pharmaceutical study and looked at the confidence intervals they usually use? They typically do a 95 to 99% confidence intervals. The best of studies do 99%. How many people are you going to give a drug? Like COVID-19, COVID vaccines? Like billions, right? So if you only have a 99% chance of being right, is that going to be okay? Probably not. You have a pretty, like, a reasonable shot of really screwing this up. Okay. So if you're if you're doing something a billion times, you better give yourself a couple extra standard deviations there. Okay. We need to be somewhere down here, don't we? We can't get here, so that's just not doable. But probably need to be a little higher. Why is the Y values, by the way? What is the Y value telling you? So before I was talking about these areas under the curve, right? And we were actually talking about from 0 up to that value of Z. Okay? All added together. Right. The Y values are the literal value on the Gaussian curve here. Okay, that's the Y values. So for example, 1Y is this one right here. Okay? Notice the Y values never go above 0.4 because you have to distribute your population, right? In a Gaussian curve. Now, one of the other things, what if I wanted the like percent population that might be outside that? So the percent population between Z1 and Z2. Anybody know how I can get that? If you're going to do it graphically, how would you do that? Let's say we're doing -1 and -2. Well, you just take that area between them, right? So if we're looking at this table, instead what you would do is you check the difference between 1 here and 2 here, right? And that would be the area between those. Okay? Everybody good with that so far? Okay. Do you want to try an example? All right. Well, guess I'll take that as a yes. Like, don't be terrified of it. Come on. This is like a real example of what you'd use this for, by the way. Like you could predict that the how many murders does the worst offending 5% of the United States population commit on average? That's an actual figure that they figured out with this. As it turns out, the majority of murders. Figure. It's a really extreme Gaussian curve of murders. Would you all want me to post videos that are interesting about this material? Because there's actually a really cool economist that analyzes statistics for like social stuff. and it does a really good job of explaining how this stuff interrelates to like social issues. But I don't know if I want to post that. I feel like I could trace back and get me in trouble. I forget his name, but really cool guy. Uh, Black guy has dreads. University of Chicago. What was his name though? Hmm. Hmm. Look up his name. Very neat guy. Okay, folks, I'm gonna start moving ahead. So, how many tosses of a set of 50 coins, which we have down here? Probability theory predicts the mean of 25 heads, 25 tails, of course. Standard deviation of 3.54. How many tosses are expected to have fewer than 15 heads? If the 50 coins were tossed 400 tosses, which would be this one over here, right? And so you'd look at this data here, and these are the numbers we're going to use right there. So you'd want to write down on your piece of paper 24.98, that's the mean, right? And then S, the standard deviation, is 3.71. And notice right here we have the, well, what is the true value should have been if we did this an infinite number of times? Well, it'd be 25, right? Your mean would be 25 heads out of 50. And your standard deviation should be 3.54, okay? That'd be your true value. Okay. Or another way of saying this right here, this is S, right? This is X with a line over it for mean. This one here would be mu, and this is alpha, or sigma, excuse me. That making sense so far? Yeah. We're going to go on to the next part now. Hopefully you have all your numbers. So we need to express this desired interval in multiples of your standard deviations, so we can use the table for 1. And so again, we have our mean and sigma, and our mean is going to be 25 here. Our sigma is 3.54, okay? And so we go ahead and take our values here. Again, what did we actually want for our value, by the way? 15 heads right there, right? So we're going to take 15 to figure out where that is on our table. We take 15 minus the 25, and then we divide it by the sigma, which is 3.54. Okay, so that's going to be a value of negative 2.82. You will notice your table does not have a 0.0s number, so 0, 1, 0, 2 numbers. Okay, the table only has a 2.81. Right? So we're going to go ahead and just round that to 2.8. It's close enough. So we go ahead and look at the area between the mean, which is that right there, the 2.8, and that's going to be 0.4974. And then we look at the entire area because that's the far left, right? That would be everything else under the curve, 15 and under, right? And so we take that value, we subtract it off of 0.5 right there, and we get this value here for our area under our curve. So that would be 15 tosses or less. Okay. Anybody have any questions? Okay, so the area to the left of the 15 heads is going to be 0.276% of the entire area under a curve, which would be a 0.1, right? 100% of the curve. All right, so let's say we toss the 50 coins 400 times, and they expect to see 15 or fewer heads. How many times would we actually expect to see that? Well, we take that 400. You should expect to see it 0.26% of the time, right? And so you multiply those two numbers together, and we'd probably see it once. Okay? Now, that'd be like once on average for a 400 class. So you could get a class that does not see it, but they should on average see it once. Okay? Kind of the other way around. So remember, this is absolute value going off of the middle. Yes. So what we're talking about here is we're talking about this tail right here. And we move back and forth like it's tossed 50 times. So this is 25 here. 15 is over here. And then this would be 45, right? Or 40, I guess. Something like that. Exactly. Yeah. We're looking at that little tail there from the 15 down to the everything else. That making sense? No, you're good. That's one of the reasons I'm focusing on this is this conceptually is usually where people break down rather than like plugging numbers in, which is usually not where people break down on this. Okay. Okay. Does anybody have any questions about that further? Anybody confused? Okay. So we just traced out to the 15, right? And then everything below the 15. Okay. Everybody understands why we used the actual sigma and mu's here? Okay. So that would actually be our true values. If we were to use these values here, we would get something very similar, but not the same. Okay? We'd actually get a slightly off. Now, having said that, if you did that on multiple choice question, you'd probably skip the answer. If I'm being honest. But anyways, I'm teaching you the correct. Notice those were always sigma and mu's in the equations. Okay. I'm gonna skip this next one unless somebody really wants some more work on that. All right, so this right here is again that probabilities that I mentioned before. This is just the same thing we talked about before. Does anybody have any questions about that? Okay, so everything, 100% of values that you measure fall under the Gaussian curve, right? If you have a sigma and mu value, then that would be 100% of the possible results. Okay? But if you don't have a sigma and mu value, then it is not 100% of possible results. It's your measurements. Each measurement is going to be made, includes random uncertainty. This is described by the equation Sx, which is going to differentiate your random uncertainty. The more times a quantity is measured, the more confident you can be that the mean is going to be close to the population mean. So your relationship is going to be expressed by your standard deviation of your mean, which is this value right here. So notice again, that's your mean, mu, and that's x. You then have Sx over the square root of n. So the Sx is going to approach a constant value as your number increases to infinity. So as this number here increases to infinity, this is going to approach that narrow band exactly on there. Okay? Okay. Again, that ux, right? So yes, kind of. So this is going to be that standard deviation of your mean. It's a little bit different than the just standard error in the fact that it's like not a sigma. Okay. And it also isn't just a normal S because it's specifically for this value. And so you can indicate that specific value. And that's why it has an X there. Okay. So think of it a bit more like you would do this for like population 10, population 100. You'd have U10, U100, and then you'd have standard errors U10, U100. Does that make more sense? Yeah. So what you'd see is as your values here approach infinity, this value here is going to approach 0. And so that's going to mean that this uncertainty here is going to approach 0, because remember, this is the random error. Okay? Random error, if you had an infinite number of observations, would go to 0, right? Is that making more sense? So you can have things in your standard deviations that if you are actually end up being like blunders and stuff, right? Okay. This is the one you can kind of sense of what the amount is that's just coming from pure random error, because you can do it for 10, 100, 1,000, and see how this is changing. Okay. Okay, so let's talk about F-tests. Now, this is to compare your standard deviations. You're going to use the F-test. Do they cover the F-test in the 165? Not yet. It's okay. Yeah, eventually they cover it. Oh, 265. Okay. Okay. So two sets of measurements on the same quantity will generally differ. They'll differ in both their mean usually and their standard deviation. So this is actually the statistical tool to determine the probability of your conclusion. You're going to accept conclusions with high probability of being correct, reject conclusions with high probability of being incorrect. Null hypothesis is probably one of the hardest things to do, and it's the thing I can teach you the least to actually get correct, because it's very, very dependent on what you're talking about. Okay? So one of the things I want to point out is when you're doing a field, really, really check what your null hypothesis is and really think about it. Okay? Start here giving this deep thought and testing yourself. Test your assumptions. Because if you go in with a bad null hypothesis, all your math, all your stats will be junk. Okay? Okay, so this states that two sets of data are going to be drawn from populations with the same properties. Right? Again, this is oftentimes not true. Okay? So oftentimes people do this null hypothesis where it is not true, you should not have done it, you cannot tell this. Okay? Very common. Right. Am I clear that like people screw this up all the time? And so like really give this thought? Okay. So observed differences arise only from random variation in measurements if this null hypothesis is true. You're going to reject the null hypothesis if there is a less than 5% probability observing experimental results from two populations with the same value. All right. The null hypothesis is used with several tests. So two sets of data are drawn from populations with the same properties. The F-test is going to compare your standard deviation. Notice that is a sigma, by the way. So you must complete the F-test there. The t-test is going to compare your means. If you have to do an f-test, you need to do the f-test before you do the t-test. Okay? Was that covered it? Okay. Now, the statistical tables, which you'll find at 4344, these do include degrees of freedom. What was the degrees of freedom again? Parameters -1, or observations -1. Kind of depends on what you're doing, but okay. So are the standard deviations of two sets of measurements statistically different? This is how you're going to figure this out. This is going to give you F calculated right here. You have to test F calculated versus the table. Okay? So F calculated is going to equal your standard deviation from one population set squared divided by the standard deviation from the other population set squared. You always want to put the smaller standard deviation up on top. I'm sorry, bigger. So you have the whole numbers. You don't want to always have fractions. So the larger standard deviation goes on top, smaller one goes on the bottom. If they're equal, you kind of get to choose, because that's going to come out 1. Again, Where's the larger one go? On top, because you're going to normalize. Oh, shoot. Wow. Okay. Um. Okay. Now, I am willing to take part of next lecture and cover some more materials here, though you may want to sort of choose what is the things you really want to do. Okay. What are you having difficulties with on the homework, and what don't you understand? Okay. Okay. No, we basically are just going to cover Gaussian. Yeah. Because most of what you need to know, so we don't really look at populations much in analytical chemistry. What we look more on is observation sets. And so realistically, if it's non-Gaussian, you know it's not random error. And you know you need to look at your other errors. In order to get like your yeah, we're basically looking more towards. So if you know it's not a Gaussian distribution, you can pretty much state at that point that you're not random, right? Yeah. And in analytical chemistry, we can control everything. So instead of us fixing our stats to fit things we can't control, we actually fix what we can control so that'll become a random error. Then we can get better results. That make a little sense?
And so we'll be back with your opposite one.
Yes. Or we can. Did you guys want to do lunch?
I don't know. Well, I was going to use it for the time. Just it's probably easier for me to.
Okay. Yeah. Come to my office at 1 then.
Yeah.
Do you guys just want to do that then?
That'd be it.
Sure. Okay.
Okay. Perfect. Thanks.
Definitely. Did you guys manage to run Hello Water?
No.